Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I've been looking forward to see a proof of this result for some years since Durrett posed the question. And on Tuesday we had all the build-up of the tension, and today we're going to see how come that Durrett lower bound can be almost realized as an upper bound for the L-reversal chain. Ben
Okay,
Morris,
thank
please.
you. And I forgot to say Tuesday, thank you, Yuval, for the invitation. Okay, there's my title again. So let me remind you of the main theorem. So first the definition. Okay, we have this card shuffle that has collisions. So a collision is, when you do a collision with probability a half, you do nothing with probability a half, you do a transposition. And we have a random variable t such that after time t, you start matching the cards up based on what collides with what. So after time t, if two cards collide, they're matched. Two more cards collide, they're matched, and so on.
The paper on the bottom really makes us focus on the part you're trying to hide.
Okay. And then the theorem said, that was the definition of the match of a card. And then the theorem said that if for every card k, its match is lambda k uniform, so roughly uniform in some sense over all the cards that were initially above it, then for any permutation mu, so any permutation, random permutation you start with, if you run the chain for t additional steps, you're going to bring the entropy down by the sum over k, roughly a constant times the entropy that was attributable to position k. Okay, does anybody need to be reminded about any of the definitions? Okay, so this was on Tuesday. So now,
People weren't here when you can just say that the end is not entropy, but relative.
okay, so right, the ent is relative entropy. The difference between entropy and the entropy of the uniform distribution. So this will have a different sign. So when this thing gets smaller, then that actually means that the permutation is getting more random. So 0 means it's completely random. All right. So now hopefully I can bring out some ideas by doing an example. So I'll get to the L-reversal chain, but let me do the Thorp shuffle first, since the analysis is simpler. So recall in the Thorp shuffle, you cut the cards exactly in half, and then you line up the cards in pairs, and then the pairs collide. So it turns out that the card in position y, if y is less than n over 2, will collide with the card at position y plus n over 2, where now I'm making the positions go from 0 up to n minus 1. So the card in position y and the card in position y plus n over 2 are sent to 2y and 2y plus 1, determined by a coin flip, which goes where. Okay. So in this example, it's actually easier to work with the time reversal. So the time reversal is obtained by just, well, you look at this picture and turn around the direction of the arrows. So for the time reversal, if x is even, then card x and card x plus 1 will collide on a given step. And they'll be sent to either x over 2 or x over 2 plus n over 2, where a coin flip decides what goes where. Okay, so for general x, the position of of the card that was at x after one step is going to be either the floor of x over 2 or the floor of x over 2 plus n over 2, based on the outcome of the coin flip. Okay, so I claim that if little t is the ceiling of the log base 2 of n, then for any random permutation mu, if you start with mu and then you run t steps of the chain, you decrease the entropy by a factor 1 minus constant over log squared n. Okay, and before I prove this, let me just say why this gives the claimed mixing time bound of log n to the fourth. So if after log n steps you reduce the mixing time, you reduce the entropy by a factor 1 minus constant over log squared n, that means that the rate of decay of entropy per step is going to be constant over log cubed of n, and the initial entropy, the entropy of the identity, is going to be log n factorial, which is at most n log n. So how long does it take to bring the entropy down to something small? It's going to be on the order of log to the fourth n steps. Okay, so let me now prove this claim about the decay of entropy. Okay, so for this I'm going to use the theorem. So recall that you can decompose the entropy of a random permutation you can decompose it into the contributions of the different positions. So let's write the entropy of mu is the contribution from position 0 plus the contribution from position 1 and so on. Okay, now I'm going to divide these positions up into geometrically growing intervals. So this one has 1, this one has 1, now this one has 2, the next one will have 4, the next one will have 8, and so on. Now let m star be the value that maximizes the contribution of the corresponding interval. So one of these intervals will contribute more entropy than anybody else. Let m star be the index of that interval. Okay, so what we're going to do is we're going to choose our random variable t so that it gives high values of lambda for positions in that interval. So it's enough to show that there's some random variable t such that for every j, the card that's matched with j is lambda j uniform over the cards that were originally higher in the deck, where lambda j is constant for j in the good interval and 0 otherwise. Okay, so we're saying that if j, we have to design this random time t such that if j is in this special interval and I is less than j, then the probability that j matches with I is at least 1 over 4 times j. So it's roughly, so the card matched with j is roughly uniform over all cards that were initially higher than it.
You're going to say why this is enough?
So this is enough. But right, the theorem will tell us that if that now we get a decay in entropy that's equal to at least 1/4 times the contribution of the entropy of the positions in IM star. So
Which is almost 1 over log n of the whole thing.
Right, which is at least 1 over log n of the overall entropy.
Right. Wasn't there a log cube that we were trying to prove?
Well, we're trying to prove log squared. The additional factor of log comes in the actual theorem.
There was a log, yes. Right.
Right, so we get 1 log. So one of the logs comes from the fact that you're only doing 1 interval and there's log n intervals. And another log comes from the theorem. Okay, and then there was a third log, which was because I'm counting log n steps as 1 step. All right. So let me just give an example. So let's say n equals 32. It's actually easier to work things out if n is a power of 2. So let me assume that n is 32. So then the card in position x is sent to either x over 2 or x over 2 plus 16. With probability half each. So I'll call this, so basically x is sent to the floor of x over 2, but then there's this random offset that you add each step, which is either 16 or 0. Okay, and so let's assume that j is between 2 to the m minus 1 and 2 to the m minus 1. So m star takes the value m for some m at least 1. Now notice that if you have 2 cards, say the card at position 20 and the card at position 7. Now if the coin flips that determine the offsets each step are the same for both cards, then those cards are bound to collide. So say look at 20 and 7. After one step, you go to, let's say the offset is 0 at this step. It becomes 10 and 3. And then divide by 2 again, it becomes 5 and 1. And now say plus 16 to both sides. Divide this 5 by 2, you get 2. 1 divided by 2 is 0. What? Huh? You can see what's happening is that after a while you forget where you started from, and all that matters is what the offsets were, because you're dividing by each step you're dividing by 2. So after log of your initial position steps, you've completely forgotten where you were, and you just.
I mean, the offsets are feeding the higher order bits.
Exactly.
Positions,
Yeah.
so
Right.
it's fed in all the bits.
Why do you assume that they receive the same offset?
Doesn't say to.
If they receive the same offset.
Right. If it happens that 2 cards receive the same offsets each step, they are bound to collide. Okay. In at most m steps, where m is where the bigger card is less than 2 to the m minus 1.
This idea goes back to Jim Reed's in the context of the workshop.
Oh, okay. Uh-huh. Okay. Okay. So so in particular, if two cards say potentially could collide after 7 steps, assuming that all the offsets are the same, then the chance that they will collide is 1/2 to the 7th. Okay. Or if they could collide after 16 steps, then the chance that they will is 1/2 to the 16th. So this tells us how we want to design our random time t. It has to the probability that t equals r has to grow exponentially with r. So we'll start with we'll say the probability that it stops right when you start is going to be like on the order of 1/j, and then with each additional step, we have to multiply the probability of the time stopping there by a factor of 2 to cancel out with this probability that of our two cards having had the same offsets each step. So okay, so we're gonna oops. Okay, so we're gonna let our random variable t satisfy probability t equals r is at least 2 to the r minus n minus 1 for r less than or equal to m. So it starts out on the order of 1/2 to the m, and then grows exponentially with the rate 2. So then if I is less than j, the probability that the match of j is I is at least 1/2 to the m plus 1. Okay, it doesn't matter how far away I was initially from j. You know, from the previous slide, you know if I is less than j, that there's a certain number of steps such that after this many steps, I and j are bound to collide if they have the same offsets.
Does this mean that this is the first collision or j?
So here's the thing. You know that I and j will collide if they have the same offsets at a certain point. And that happens with probability 1/2 to the... I'll say that if they potentially collide after 7 steps, I'll say that their distance is 7. So if their distance is 7, then the chance that they are going to run into each other is 1/2 to the 7th. But that doesn't imply that they're matched with each other. Because the way that a match is defined is you wait until time t, and then the next card that is matched with card j after time t, the next one that collides with it after time t is defined as its match. Okay, so for any I less than j, it's some distance away from j. The chance that it will collide with j after this many steps is 1/2 to the distance. The chance that the random variable t actually takes the value that is the distance between I and j is like 1/2 to the m times 2 to the distance. Because this starts out at 1/2 to the m and grows by a factor of 2 each step. So you end up with, so the probability, maybe I should have done more steps. Probability m of j equals I equals probability that let's say the distance is between I and j is d. So this is the probability that the match of j is I is the probability that they do in fact collide after d steps. So I and j collide after d steps. But then you also have to have the fact that the time t is the time after which you start matching things together also has to take the value d. So this is so the chance that I.
So you bound this above by the probability that they collide exactly at the stopping time. So this has to be the first collision after t. This is why this is the first collision after time t.
Yeah, in this example, the after time t is just at time t, because everything will collide with something at time t.
Okay.
All right. So, yeah, I mean, I should say at, right, after time, at, because it happens at time t, times the probability t equals d. So the chance of colliding after d steps is 1/2 to the d. So, and now we've designed our random variable t such that the probability that it takes the value d is 2 to the d minus n minus 1. So then the 1/2 to the d will cancel out with a 2 to the d here. So this is at least 2 to the minus m minus 1. And j is on the order of 2 to the m. So this is at least 1 over 4j, say. Okay.
Sharp results of your crude argument.
Okay, so we're done. This is it.
Does this happen a lot that cards collide in that way by just following the same offsets? It seems very crude.
It's the only way for them to collide, is to have the same offset.
We need to get to the full position. Eventually have some, and they can be different at first, but eventually they have to be.
Yeah, that's easy to see if you. There's an equivalent description of the Thorp shuffle when it's a power of 2, where you take the position. So write the position in binary, and then each step you erase the first bit, and then put a random bit at the end. And then that's the new position. So what happens is after a while, it doesn't matter what was at the beginning. All that matters is these new bits that you're writing in.
Reverse direction.
It's reversing direction all the time to keep us
Oh, I thought it was, you don't shift to the left, you shift to the right? Okay.
If you want to read this as a number,
Uh-huh.
then you have to...
Yeah, okay. Right.
Using the cards on top, lower index.
Well, this was, I was,
Alright, both conventions are used, but one day and beginning.
okay, so let me, okay, so let me, anyway, so it's kind of nice because you're just verifying a condition that it involves only the pairs of cards. So kind of like when maybe you have some card shuffle, you might reason at an upper bound for the mixing time by just thinking, well, how long does it take this shuffle to mix up pairs? But what this does is it says, well, that I can actually prove an upper bound on the mixing time by just considering the behavior of pairs. Okay, so if there are no more questions on this, let me do the other example. Okay, right, here it is. Let me just remind you of the definition of the L reversal chain. So you have n cards arrayed in a circle, and then each step you'll choose an interval of cards of length at most L and reverse it. So if you consider a single card, it will move, when it does move, it will move on the order of L, a distance on the order of L. But, so it'll have to be moved on the order of n squared over L squared times before its position is random. But it's only going to be moved with probability on the order of L over n each step. So you need to, so to figure out the time to randomize a single card, you take the n squared over L squared and you multiply by n over L, and you get n cubed over L cubed. And then you have to multiply by an additional factor of log n, because there are n cards that have to be randomized. So this can all be made rigorous using David's argument, using eigenfunctions and so on, but I'm trying to give a heuristic. So you know the mixing time has to be at least on the order of n cubed over L cubed log n. But then now consider pairs. So if a pair of cards are initially adjacent, then they will remain adjacent after one step unless they were separated by the interval that was reversed at that step. Each step, an interval will only reverse, will only separate at most two bonds between adjacent cards. So by the coupon collector problem, by the coupon collector problem, the time to separate all the bonds is on the order of n log n. So Durrett argued that Durrett proved that the mixing time has to be at least on the order of the maximum of n and n cubed over L cubed times log n, and conjectured that this is also an upper bound. Okay, so basically, since the argument I just gave for the lower bound, it just has to do with pairs, and in considering the behavior of pairs, we should expect that maybe our new theorem could also prove something about the upper bound. Okay. So. Okay, so indeed we get the following corollary of the main theorem, which says that the mixing time is big O of log cubed and times this strange max of n and n cubed over L cubed. So it's the conjecture with an extra factor log squared n. Okay, and the proof will proceed in a similar way to the Thorp shuffle. So first, we're gonna decompose the. So we'll start with some arbitrary permutation mu. We'll decompose the entropy of mu according to the positions. Now we'll break the positions into geometrically growing intervals, starting with initially the first interval is of length L. So I guess it goes L and then of length 3L and then 9L and so on. So we must have the contribution from one of the intervals at least 1 over log n times the overall entropy. And here I'm using I introduced some new notation here. All right, that the entropy, so you have some random permutation mu, and I'll say that the entropy of mu on AK and mu comma AK, this is my notation for the contribution of the indices in AK to the entropy of mu. So this the sum over j in AK of EJ equals the contribution of AK to the overall entropy. So now we break down according to the value of K. If K is 1, so the most of the entropy comes from the, or the highest amount of entropy comes from the first interval, then it actually works out. We can analyze this using standard techniques. So imagine that we're just okay. So we want to say that we get a nice decay in entropy. So if you just consider the case where a lot of the entropy comes from the first L positions, then here we're notice that if you switch an interval and then you switch another interval that's exactly the same, only one smaller on each side, then that has the effect of keeping everything the same, only reversing the cards that are in the outer interval and not the inner interval. And when the length of the interval is comparable to the number of cards, then this is a well-known card shuffle. It's called random transpositions, and like everything is known about it, so the rate of decay of entropy is known. So I don't have to do anything using my theorem for this case.
That was when you make this successive pair of switches.
Oh, right. So so that you can use what's called comparison techniques to. So if you can simulate a known Markov chain using moves of your Markov chain, then you can get.
But this is not a move, right? Because L is fixed.
No, L is the maximum length of the interval.
The maximum.
Switch a uniform length up to L.
Yeah. So since I can simulate random transpositions using two consecutive moves of my Markov chain, I can use what's called comparison techniques to compare the log Sobolev constant for random transpositions with the log Sobolev constant for this for the L reversal chain in the case where the length of reversals is comparable to the number of cards. So I can get a bound in the decay of entropy in that case. But anyway, my point is, in this case, it's completely not related to this talk, so I'll just move on to the case where
K equals 1. That reduces to random transposition. I don't get it.
So then the length of the interval where the action is the same as the length of the interval that you're flipping. So it's like
Same. So with the L is fixed. Right? So you say K equals 1 means that most of the entropy is
or at least one over log n.
one over log n.
So we put down our cards according to mu. Once we've gotten to the top L cards, it still looks random, up to the factor log n. So that means that we just need to consider the effect of the chain on the randomness of the top L cards.
Okay.
Okay, so now let's assume that k is bigger than 1. So in this case, we're going to use our theorem. So we have to, so we want to come up with a random time t such that the distribution of the card matched with j is roughly uniform over 1, 2, 3 up to j. So how long are we going to want to run the chain if j is in AK? So suppose we have Okay, so we have our A1, A2, and so on. Remember, these are geometrically growing intervals. ... So suppose we have some j in AK. So since these intervals are growing geometrically, the value of j is going to be roughly the size of AK. So j is up to a constant factor is just the size of AK. So how many steps do we need to run the chain such that the card that is matched with j is roughly uniform over what was initially higher? Well, each time you it's like the analysis from before. Each time you move j, it's going to move on the order of L. So you need to move it on the order of n squared over L squared times. On the order of size of AK squared over L squared times. And you touch it with probability on the order of L over n each step. So the number of times you're going to want to move it, the number of times you're going to want to do your process is going to be like size of AK squared over L squared times n over L. Okay, so if we let t be some constant times size of AK squared over L squared times n over L, and so here it actually works out that we want to so I could probably just let the random variable t equal little t, but I wasn't able to prove that it works in that way. So the only way I could get things to work is if I let t be uniform over 1, 2, 3 up to little t. So now what's the chance that that I is matched with j if I is less than j? Well, if I run the process for this many steps, then the distribution of what's close to j after that many steps is going to be roughly uniform over 1, 2, 3 up to j. But there's only going to be a collision involving j with probability on the order of t over n. Because there's a collision each step. So if I run the process for only little t steps, there's only the chance that there's a collision involving j is only on the order of t over n. So the distribution of the match of j is going to be lambda j uniform, where lambda j is constant times the max of t over n and 1. Right? Okay.
But you don't need card J to collide exactly in the J step exactly in the T step for this match to occur.
Right. We need it to collide by time t. So since we only have t chances for it to collide, then the probability, you have to multiply by the t over n, because you only have t chances.
Wait, so could you explain that again? Why you get lambda j uniformity for the card?
Okay. So so you can see where this number comes from, right? This is how long it takes to kind of make the distribution of card j roughly uniform over 1, 2, 3 up to j. Okay, but that's not enough to imply that it even has a match. So if I were to run the process for that many steps and look at some card that's nearby, it's going to be roughly uniform over 1, 2, 3 up to j. Okay.
Now I see.
Yeah. But I also need for card j to have collided with something.
So collisions here you get just by doing these two successive intervals, one shorter by one from the other? What's the source of collision?
So remember, I gave an alternative definition of the reversal chain where each step you don't actually know. You can narrow the reverse interval down to two, one of which was one bigger than the other on each side. So roughly speaking, okay. So the original definition of the L reversal chain is take an interval of length at most L and reverse it. The new definition is take an interval of length at most L and reverse it, and then with probability of half, change your mind and decide that you don't really want to reverse the two cards on the outside of the interval. So, in other words, reverse the interval, but then do a collision of say if A and B are the ones on the outside, do a collision of A and B after reversing the whole interval. All right.
You have to start with not exactly the uniform distribution for your first length.
It's basically the uniform distribution, except that at the ends there's some issues. But okay, so but the point is, there's only two cards that collide at any step. So if you're running the process for only little t steps, you will only at most little t of your cards have, or 2 times little t of your cards have collided. So that's why you have to multiply by this factor of t over n when t is less than n. Okay. So then, all right. So where's my next slide?
Your t is here typically much less than n, and
once t is bigger than n, that we don't have to worry about this issue. So, but by the way, you're wondering where the max comes from in Durrett's conjecture. It comes from this min, and this min is a lower bound on the decay of entropy. So when you turn that into a upper bound for the mixing time, you get a max. So if we kind of follow this min around, and in the end it'll show us where the max is. Okay, so then by the theorem, that the decay of entropy after little t steps is going to be. So let me write lambda for what I called. Okay, so lambda is this quantity that I wrote on the previous slide, constant t over n min 1. So the decay of entropy is going to be at least a constant times lambda over log n times the entropy attributable to the kth interval. And remember, we're assuming that that's at least a fraction 1 over log n times the overall entropy. So the entropy decays by a factor 1 minus constant over log squared n times the initial entropy, which is at most e to the minus constant lambda over log squared n times the initial entropy. So, but remember, this is the decay in entropy after little t steps. To get the rate of decay of entropy per step, we have to divide this by t. So we get 1 over. So now I'm plugging in the value of lambda. So I'm plugging in the value of lambda, and over here I'm just dividing by t. So c lambda over t log squared n. And here I'm plugging in the value for lambda, which is constant times t over n min 1. Oh, and there's 2 c's, but this c is c squared equals c for today. Okay, so take this, divide by t to get the rate of entropy decay. And it's equal, if you substitute in for lambda, you get 1 over c log squared n times the max of n and t. Because if you have a min and then you do 1 over it, you have to change it to a max. And now I'm using the fact that t is at most n cubed over L cubed. So we can replace the t by n cubed over L cubed. And this gives us a bound on the decay of entropy per unit of time over the medium term. And again, the initial entropy is n log n. So to get the mixing time, you take the rate of decay of entropy and multiply that by, or 1 over the rate of decay of entropy, multiply that by log of the initial entropy, and then you get what I claimed it was. Log cubed times max n over L cubed.
Where was can you remind us the value for t and how?
Okay, so t, I erased it. So t was a constant times the size of ak squared over L squared times n over L. And the size of any interval is less than n. So this is less equal constant times n cubed over L cubed.
So the only time this is sharp is if the relevant interval happened to be the last one.
Right.
So it seems like you can gain something there by making the last one shorter.
The last ones.
The last interval.
Well, this
Why just the last?
What about the second?
Well, so making them not grow geometrically, but divided into log n intervals some other way.
But this size of AK is just an approximation for the value of j. So this is like j squared over. This is like j squared over L squared for some value of j in AK. Okay, so there's my talk.